started. We're going to pick up where we left off last time. So last time we had some technical difficulties where we couldn't get I couldn't get this projector to work, right? So unfortunately there's not a recording of last lecture. I had to do board work. But we covered these 6 reactions here. All right, so we want to be able to predict the product of these 6 reactions here. So everybody take a second and see if you can't do that based on what we discussed last class. All right, so let's go through these. So these are called electrophilic aromatic substitution reactions. You'll see that abbreviated EAS. The key word here is substitution, right? So unlike our reactions of alkenes where we had addition reactions, for these reactions we're going to be substituting one of the hydrogens on that benzene ring for something else, right? We're going to swap it out and replace it with something else. So in the case of Br2 and aluminum bromide, what do we put on there? A bromine, right? So the sort of hint is what's going on top of the arrow. All of these reactions are going to require a catalyst. So there's going to be something sitting underneath that arrow as well. But the real key is what's going to be on top. That tells you what you're adding. And in this case, it would be a bromine. And just a single bromine is being added, right? So you use Br2, but there's only one bromine that's being added. And again, you're substituting the hydrogen that was on that benzene ring for that bromine. All right, so then by analogy, if we use Cl2 and aluminum chloride, we're going to get substitution of a chlorine. All right, so both of those are these halogens that we can put on there. Importantly, right, we get lazy. How many lone pairs are there on each of those halogens? 3, right? So all of our halogens will have 3 lone pairs if we're being good. It's just important to remember that they're there, right? They all need their complete octet. They got 1 bond. That means they have to have 3 lone pairs. All right, nitric acid with a sulfuric acid catalyst. The key, again, is what's sitting above that arrow. This is how we add a nitro group on there. All right, so notice that we're using nitric acid HNO3, but it's only NO2 that's being added. If we use fuming sulfuric acid, we put on what's called a sulfonyl group. SO3H. So again, we're using H2SO4, but we're only adding SO3H. So in both of these cases, we're losing an OH from our original, what we started with, right? So HNO3, we have one less oxygen, one less hydrogen. Same thing for our H2SO4. When we put it on there, we get one less oxygen, one less hydrogen. Okay? These next ones these are called the Friedel-Crafts reactions, and importantly, you get to form a new carbon-carbon bond. So what I'm going to do is I'm going to look at my substrate here. I have these 3 carbons that I'm going to add. Okay? And importantly, the place that's going to be attached to my benzene ring is the carbon that used to have the chlorine on there. So when I draw this out, I have my benzene ring, but now I'm going to attach this 3-carbon compound. Again, I got to attach it at that middle carbon where that chlorine was. That one right there, right? The carbon that used to have the chlorine on it now becomes stuck to the ring. Same thing with the last reaction here. The only difference is that now that carbon has an oxygen double bonded to it. Whoops. But same idea. I'm going to draw my benzene, and now it's going to have a new bond. I'm going to replace the chlorine. And so what's going to be bound to my ring? It's going to be this, right? So again, the ring is attached to the same carbon where that chlorine was. So in both of those reactions, you create these new carbon-carbon bonds between your benzene carbon and whatever you're attaching. Again, both of these used to have chlorines on them, right? I colored that carbon in blue. That is what's being attached to the ring itself. All right, so if you start out with a 3-carbon compound, you're going to get 3 carbons added onto the ring. All right, let's practice that one more time here because I know that those ones are trickier than the other ones. All right, so we're starting off with benzene. We're going to add something to it. Let's actually put it here. All right, and when you finish up, do me a favor, go back and count carbons on both sides of your reaction. Make sure you have the same number of carbons. It's a really easy check that you can do to make sure you haven't made a stupid mistake. All right, so I'm going to start by just putting down my benzene. And now I have to add this compound to it. Again, I'm going to make sure to attach it at this second carbon here that has that chlorine. Right? So I got to draw a bond to that carbon. That should be my blue carbon. So on the one side, I have one carbon sticking out, and then 1, 2, 3, 1, 2, 3. All right, and again, counting carbons, really easy way to make sure 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. All right, great. All right, same deal over here. You're gonna start with your benzene. Now I gotta attach all this business going on. All right, all those carbons, and importantly, the portion that's going to be attached to the ring is that carbon there that used to have the chlorine. So draw that with the oxygen double bonded, and then I need to have 1. And then here is a 6-membered ring. Okay, so kind of the generic way to write these reactions would be to say something like RCl, where the R can be any amount of carbons, right? It can be something small like a methyl group, just 1 carbon. It could have 400 carbons on it, right? That R group could be as big as we want. As long as there's a chlorine attached to it, we can attach it to our benzene ring. All right, same thing for this last one. Except for now, our chlorine is necessarily bound to a carbon that has an oxygen double bonded, and then the back end of that could be whatever we want it to be. All right, so these are these same 2 reactions kind of generically written. And again, R just stands for whatever you want it to. Okay, cool. So these were these 6 reactions we introduced last time. So now we're going to talk about mixing and matching these reactions. So what do I mean by that? Well, so let's say that we had started out with benzene all by itself. If I react it with Br2 and aluminum bromide, what am I going to get there? What am I going to put on? Right, I'm going to look at what's above this. This gives me this hint. It's going to be the bromine. All right, but now let's say that we want to do another one. This second reaction, what will that do for me? What do we call that group? A nitro group, yep, so this will stick a nitro group on there. But the question is where, right? There's 3 potential products that I would get from this reaction depending on where that nitro group goes. Could go right next door to the bromine. Could be one removed, or it could be on the opposite side of that ring. All right, so which one of these am I actually going to get as my product, right? So this is the question that we're going to address here today. Remember, the last thing we did last time is we actually named these different positions, right? So the ones right next door to whatever's already on the ring, we call ortho positions. All right, so the ones that are located, the carbons that are located right next door to that bromine are the ortho positions. One removed are what we call the meta positions. And then the one on the very opposite side of the ring, we call the para positions. All right, so where does that nitro group go? Does it go to the ortho position, the meta position, or the para position? Okay, that's the question we want to ask. So it turns out that each of these substituents have what's called a directing effect, meaning they're going to direct incoming substituents to a particular position. Some of them are ortho-para-directors, other ones are meta-directors. You're always either ortho-para or meta. There's never just an ortho-director or something like that. So our directors, our substituents are going to fall into one of two categories, either ortho-para-directing or meta-directing. Okay? So if anything has a lone pair on it, it's going to be an ortho-para-director. So for example, if there's a nitrogen directly bound to the ring, or an OH group, any sort of an oxygen directly bound to the ring, or a halogen directly bound to the ring, any of those substituents that have a lone pair on them will be ortho-para-directing. Okay, so it's easy to spot whether it's an ortho-para-directing because again, they'll have that lone pair. But this is sort of what I was getting at before, where we get lazy and we don't necessarily draw the lone pairs, so it's important to remember that our halogens, oxygen, and nitrogen, they will all have lone pairs on them. All right, and then the last group that is ortho-para-directing, that's kind of an exception to that rule, are our alkyl groups. All right, so any sort of an alkyl group, however big or small, 1 carbon or 1,000 carbons, those will also be ortho-para-directing. All right, so if we go back here, again, we sort of asked ourselves what would be the actual product here. So if I label these A, B, and C, one of these don't belong, right? Remember the bromine that was on this, that was originally on this, had these 3 lone pairs, making it an ortho-para-director. So which one of my 3 products can I nix is not going to be there? A, B, or C?
You said it's not.
One of them is not going to be there, right? Because bromine is an ortho-para-director.
B.
So then B is not actually going to be a product of this reaction. I'm only going to get the products where the nitro group is on the ortho position and the para position. Notice that it's the bromine, the thing that was already on the ring, that's going to direct the incoming substituent. The nitro group isn't the one that decides where it gets to go. It's what's already on the ring, that bromine, that's going to direct the incoming substituent to a particular place, right? Again, bromine is an ortho-para-director, so we're going to get the ortho and the para product, not the meta product. Okay? So again, our ortho-para-directors, they all have these lone pairs on them. So if a lone pair is sitting right next to the ring, you know it's an ortho-para-director. The exception are these alkyl groups, which are also ortho-para-directors. Right? An alkyl chain of any length. When we go to our metadirectors, so first of all, one common feature of the metadirectors is when a carbon that's double bonded to an oxygen is attached to the ring, right? Does anybody remember what we called these bonds here? CO double bonds? Probably gonna hear me say it a bunch, so let's just flesh it out here. C, double bonded to an O, these are called carbonyls. It's called a carbonyl bond. Okay, so again, you're probably just gonna hear me say it, so let's put it in our vernacular here. If there is a carbonyl carbon bound to that ring, as is the case with all of these groups here, that is a metadirector. Okay. The other 3 here we just kind of got to know. Importantly are these sulfonyl groups and the nitro groups, right? Because we know how to make those. Right? We know how to stick a sulfonyl group on there. We know how to stick a nitro group on there. Both of those would be metadirectors. All right, and then the last one is a carbon that's triple bonded to a nitrogen, what we call a cyano group. All right, so in all these cases, you have something that's like double or triple bonded to an oxygen or a nitrogen. All right, but nonetheless, these are all our metadirectors here. All right, so first of all, let's just see if we can spot orthopara versus metadirectors. All right, so I'm going to put down a bunch of compounds, and you're going to tell me whether the substituent on there is orthopara or metadirecting. Guys are going to be hexagon drawn experts by the end of the chapter. All right, so let's go over these together. This one here, my first one, is that going to be orthopara or metadirecting? Who thinks it's orthopara? Who thinks it's meta? So this one would be an orthopara director because nitrogen has a lone pair. Remember, nitrogen will have 3 bonds and 1 lone pair. What's up?
It didn't write.
Oh, I just put the lone pair on there. I didn't actually write orthopara yet. Okay. What about my chloro group? Orthopara or metadirecting? So again, we got these lone pairs on my chlorine, so this is an orthopara. para director. What about this thing? This thing would be called a carboxylic acid, which would that orthopara or meta-directing? All right, so now we have this carbonyl carbon that's attached to the ring, so this is a meta-director. All right, so first of all, let's look at the similarities between these next two examples here. They're like the same functional group, just like attached differently, right? So one of them sort of swapped from the other one. Both have this oxygen attached to this carbonyl carbon. My first example is going to be what? Orthopara or meta-directing? So this one's going to be orthopara because this has a lone pair on the oxygens, right? So anytime that ring is attached to something with a lone pair, it's going to be orthopara directing. So there is that carbonyl carbon for sure, but that carbonyl carbon is not the thing that's attached to the ring. The oxygen is, right? If you got a lone pair attached to that ring, it's going to be orthopara. When we go to the other example though, we have that same functional group but kind of swapped, and now my carbonyl carbon is attached to the ring, right? So this one would be the meta-director, because I have this carbonyl carbon attached to that ring. Our nitro group, what's that one?
Meta.
That is a meta-director. That's just kind of one of those ones we just kind of got to know here. What about this group here? This little 3-carbon attached here. Orthopara or meta? Who thinks it's orthopara? Who thinks it's meta? So this would be an alkyl group, right? It's just carbons and hydrogens. So this would be an orthopara director. Remember when we looked at our substituents here, we said that all of our orthopara directors had these lone pairs except for those alkyl groups. Those alkyl groups we also have to just know are orthopara directors. All right, the OH group, orthopara or meta? How many lone pairs are on that oxygen? 2, right? So 1, 2, so we got lone pairs located right next door to the ring, so this has to be orthopara directing. All right, and just like our nitro group, we just kind of got to know for this sulfonyl group that it is meta-directing. What's up?
So when drawing the reactions, like on the previous page, do we have to draw both the ortho and the para?
Yeah, when it's an ortho-para director, you will always have 2 products, the ortho product and the para product. All right, so now let's tie this all together here. When is this going to be important? So for example, again, now we're talking about mixing and matching these particular reactions. Let's say first, I did my bromine and aluminum bromide. And then afterwards, oh, we already did that one. I lied. Let's do chlorine and aluminum chloride. That's not a 3. And then next we'll do our fuming H2SO4. All right, let's do this one together, and then I'm going to put one up there for y'all to do on your own. Okay? So the first thing we're going to do is this first reaction, which tells me that I'm going to stick a chlorine onto my ring. All right, so the first step, I'm going to get this product. Right, that's step 1. And then I have to ask myself, is this an orthopara or a meta-director? So in this case, how many lone pairs are on this chlorine? 3. So I have these lone pairs located right next door to the ring. So this is going to be an orthopara para directing group. Meaning whatever I add next is going to be added to the ortho and the para positions. All right, so that would be, I could pick either one of these two or this bottom one here, right? So I'm gonna have to draw both the ortho and the para product. I didn't leave myself much room. Just put them down here. All right, so then I gotta look at my next reaction. All right, that's telling me I'm gonna add one of those SO3H groups. And I need to stick it on the ortho position. And the para position. All right, so this would now be the product of step 2.
I have a question. Does
Yeah.
it matter where we put the first product, like when we put it on the ring?
No, you could put it at the top, right? You could rotate this molecule 60 degrees, 6 different times, and it would all be the same thing.
Okay.
Like similarly, if for my ortho product, if instead I had picked this carbon over here, that would have been equivalent. Okay, so these are why these matter, right? Because again, we're going to take these 6 reactions, but we're going to start mixing and matching them, and the order matters, what we're going to see. So now let's do the same reaction, but let's do it in the reverse order, where first I do my fuming H2SO4, and then I do the chlorine. So everybody take a second and see if you can give me my products of this 2-step reaction here, product or products, we'll see. All right, so now we're going to do the first step, which is going to be adding that sulfonyl group, the SO3H. Now I got to look at that substituent and ask myself, is it ortho-para or meta-directing? This is a meta-director, so I'm going to have to put that incoming group on one of the meta positions. Okay, so notice that these are the same 2 reactions, we just did them in a different order. And based on the order in which we do the reactions, we get different products. Right, for the first one, when we do the chlorine step first, we get that ortho-para product. When we do the sulfonyl step first, we get the meta product. All right, so again, it's these same 6 reactions, but now we're mixing and matching them. Okay, so what's another type of pain in the ass problem that I can do? So first of all, on the exam, you'll be given something like a word bank of all the different reagents that we could possibly use. All right, so again, it's not about memorizing them, it's about being able to recognize them. Okay? But I could ask you something like starting with benzene. How do we get to, for example, what would be a good one? All right, so I want to know what reactions you would do in order to create this product here. Okay, so how do we go about doing this? First of all, I'm going to look at each of these substituents. That's going to tell me which one of my reagents I'm going to need to use. I can think about the order here in a second, but step one, I just got to identify the reactions that I need. Right, so for my NO2 group, let's go A, B, C, D, E, F. Which one am I going to use? I'm going to need A and C, yeah. So the first one, well, so for my NO2 group, I'm going to need this one, okay? And then for my BR, I'm going to need A. So let's just grab these two, put them down here, okay? So I got my two reactions that I'm going to need to carry this out. So now the question is, what order do I do them in, right? So then I got to look at my product. I got to ask myself, are these two groups ortho, meta, or para from one another? What are they in my product? Not meta. Para, right? On the opposite sides of the ring, those are the para positions, right? So if I just go through and label these two would be ortho, these are meta, this is the para position. I guess relative to that nitro group. But yes, these are on opposite sides, so they are para to one another. All right, that means that the first thing I need to do needs to be that ortho para director. I need to put the ortho para director on there first, because that'll direct that incoming substituent to that para position. So in this case, the first thing I'm going to do is my bromine reaction, because bromine is an ortho para director. So if I stick that on there first, it will direct the incoming nitro group. All right, so 1, 2. We'll direct that incoming nitro group to the para position. All right, so now I'm going to give one for y'all to do on your own here. I'll actually move this down so we can see our word bank here. Oh, bummer. right, so for the nitro group, we said that's going to be this reaction, reaction C here. That's what puts a nitro group on there. What about this thing here? Which reaction am I going to need? It is indeed an alkyl group. So which one of these reagents do I use to put on alkyl groups? A, B, C, D, E, or F? E. Right, so I'm going to need to use this reaction here as well. All right, and I can explicitly, right, it's not just R at this point because I know what's on the other end here. So I need to put that 4-carbon with the chlorine on carbon 2 because that's what eventually gets attached to my ring. So these are the two reactions that I'm going to need here. So now the question is, how do I order them? Which one do I do first? So again, I got to look at my product. And my product, are these two substituents sitting ortho, meta, or para to one another? Yeah, this one's meta. So that means the first reaction needs to be one that puts on a metadirector. So that means that the first thing I need to do is put that nitro group on there. That nitro group is a metadirector. And then I can attach that alkyl substituent. All right, so we got to identify which reactions we're going to use and then figure out the order based on the position of my substituents in my product. Okay. Bless you.
But we would get like that bank of reactions.
You do get the bank, yep. So again, it's not about memorizing them, it's about being able to sight recognize them. All right, and then maybe like worst case scenario because it uses some of the harder reactions. All right, so what are my two reactions that I'm going to need to use? A, B, C, D, E, or F?
B and F.
All right, so these are the two that I'm creating new carbon-carbon bonds. So that would be this one that puts on an alkyl group, as well as this one. Okay, and I can explicitly draw in what R is here. Whoa. For my alkyl group, that's just a single carbon compound, right? I've only attached one carbon here, so that would be like a methyl group. So CH3Cl. For my other one, I want to make sure to have 1, 2, 3, 4 carbons on that chain. So 1, 2, 3, 4 carbons. Okay, then I got to look at my product and ask, are these ortho, meta, or para to one another? In this case, they are These are right next door to one another, so these are ortho, which means that the first thing I'm going to need to put on there is an ortho para director. Right? Which one of these two groups is my ortho para director, the top or the bottom? Right, that alkyl group. The other one, because it has this carbonyl carbon, would be a metadirector. So the first thing I'm going to do is put on that alkyl group, and then I can stick on that other one, right? And that'll direct that incoming substituent to the ortho or para position. Well. Cool? All right, so that's pretty much all I got for you today. Real quick, just to summarize this chapter, there was two main skills that we kind of learned here. First of all is being able to classify compounds as being aromatic, non-aromatic, or anti-aromatic. That's a big part of this chapter. The other one is these 6 reactions and being able to mix and match them, right? Keeping in mind what are our ortho-para directors and what are our meta-directors. That's going to dictate what my product is depending on the order in which I do them. All right? I apologize I don't have your exams for you. They're taking me longer than I thought, but I'll have them for you next time, all right?